Example 2 here is asking us to do the exact same thing. And so now we're finding the inverse of f of x equals 2 to the negative x power. Again, with lesson 3, module 4, lesson 3, we have already graphed this. So if you want a step-by-step of how to graph this, go back and visit this video. But I'm assuming we remember since it was just 2 lessons ago. So we have our values and we have our graph. Now remember that when we did this, we rewrote this as f of x to the 1/2 power, or to the, sorry, f of x equals 1/2 to the x power. So let's kind of keep that in mind, especially when we go down here and solve algebraically. Okay. Now, when I'm solving this graphically, and we're going to go through this a little bit quicker because we literally just did the exact same thing in lesson 1. All we do is we rewrite our inverses by switching our x and y. So my x column here will become my y column here. And my y column here will become my x column here. Okay, and actually before I plot this, I'm kind of jumping ahead of myself. Let's kind of forget about this for a second. While we have this function here by itself, let's go over its domain and range. So as we go from left to right, we go from arrow to arrow here. So my domain is all real numbers. My range of my function, as I go from the bottom to the top, I hit this horizontal asymptote first. And then the last thing I hit is this arrow. So that's 0 to infinity, which when we graph this, that's exactly what we found here for that domain and range. And we have that horizontal asymptote right here at y equals 0. Okay. So now that we've kind of identified everything for my exponential, let's come over here back to the log. So one more time, we got all of these by switching our x and y. So let's plot those. And before we connect, we need to identify that asymptote. Okay, so there's my points. And that whole, or that vertical asymptote is going to be perpendicular. And give me a second, my highlighter ran away. Okay. And that same vertical asymptote as we did last time right here along that x or that y axis. And this is at x equals 0. So when we connect those points, we are not going to cross an asymptote. Now my graph's not good because it does look like it's kind of bouncing and going further away. So to be accurate, something a little bit more like that. Okay, and again, we have this line of symmetry of y equals x, and we can verify that every point is equal distance from that line of symmetry. Okay. So we can use the graph to get the domain and range, but from last time, we can see that the domain and range just switch places. So here, my domain will become what my range was. So this is 0 to infinity. And if you go from left to right, we go vertical asymptote to our arrow, so to infinity. And our range and domain will switch places. So this will be all real numbers, which as we go from the bottom to the top, you hit arrow and then arrow. Okay, and then lastly, my vertical asymptote that we already talked about is at x equals 0. And to make this complete, let's make sure these are labeled. So the red is my function, the blue is my inverse function. Okay, so I think we've done everything graphically that we need to do. So now algebraically. So if I rewrite my function, I'm going to rewrite it with this 1/2 to the x power. Start with f of x equals 1/2 to the x. Step 1 is to replace f of x with y. Step 2 is to switch our x and y, or interchange our x and y. Step 3 is to solve. So again, I have no way of solving for y when it is in the exponent position. So we need to rewrite this. Excuse me, I'm sorry. Okay, when we rewrite this as an equivalent log expression or equation, we go from base to the other side of the equals. So this is an exponent with a base of 1/2. So this is log base 1/2 x, and that will equal my exponent equals y. Do not stop there. This will get you most credit to get all your points. Step 4 is to rewrite y using your inverse function notation. So the inverse of f of x is log base 1/2 of x. So we know what the graph looks like, and now we know what to call that inverse. If you notice here, those bases are never changing, right? From the previous page, when I had an exponential with a base of 2, I have a log with a base of 2. Here, when I have an exponential with a base of 1/2, we have a log with a base of 1/2. The bases will always be the same. Now, this exponential graph was an exponential with a base between 0 and 1. And when you have a base that is between 0 and 1, these graphs will be always decreasing. Okay, and you can see both of these graphs here are decreasing. This function is decreasing, and my log right here is decreasing. So both of those are decreasing functions. Now to kind of bring up Desmos again, I'm going to take away all of these that had increasing functions. Here we have a base of 1/2 or 0.5. Okay, which is 1/2. So then if I have a log with a base of 1/3, which is 0.3 repeating, we have this one. This one's 1/4, and this is 1/5. So you can see those are all decreasing. Now, no matter what, they have that same x-intercept at 0, 1, and that same vertical asymptote right there at x equals 0. And no matter what that base is, whether there's an increasing or decreasing function, they all have that in common. The same y or x-intercept and that same vertical asymptote.